Obviously, I read his bio, and he's a professor at electrical engineering at MIT. And he has done the usual things, get lots of awards, NSF awards, and everything else. But the reason he's here is because a few months ago we discovered, some people in the lab discovered and brought it to my attention, a really fabulous paper that kind of took the algorithm behind ChatGPT and used some of the mappings that were known, kind of some aspects of it before, to kind of a statistical mechanics language. At least that's how I interpreted it. And then he showed that there is actually a synchronization process, and in the end ended up mapping the project to the VCheck model. And historically, that was very exciting for me because VCheck was my master's advisor, right? So we worked ourselves through the paper actually in the lab, but we wanted to hear from the source.
Okay.
So thank you very much for coming, and we can't wait to hear how you did that.
Thank you so much. Yeah, wow, that's too generous. And I usually right. So anyway, so I think one thing I should apologize for is when I reread this email today, the invitation email, it says the talks are strictly limited to 30 minutes.
It's okay. It's
and
okay.
So
this is an open end.
Yeah. So mentally I started cutting the slides, but I'll undo the
Don't
so,
worry.
Okay. So the important thing is this is a joint work with two postdocs who were visiting postdocs. Now both of them are professors. So they were visiting MIT. So Boris and Vyshkovsky and Cyril Letruit, and with my colleague in the MIT math department, Philippe Regolet. Right. So okay. So let me again. I think this is an informal setting, right? Feel free to interrupt. I mean, I'll just tell you what I think is important in this project. I didn't realize you guys actually read the paper already.
That's
so,
okay.
Maybe something will be redundant. Okay. Right. So my talk plan is the following. So I'll tell you the high-level thesis started this project, which is that we believe transformers are good because they're generating cluster representations. I'll tell you the dynamical system model we came up with to analyze this. I'll show you some simulations. And we'll do some theory. We'll see some emergence of gradient flows and synchronization. Okay. So first of all, let's start with neural networks, right? So there are a great many neural networks in existence, but for the purpose of this talk, what's important is that they are complicated maps, right? Usually represented as some kind of network or as this architectures. Right. The important thing is that they take some input, high-dimensional input. Think of the image rasterized, right, in the pixel space, right, and then they produce some output, right? Typically different dimension, but sometimes the same dimension. Okay, so that's what we need to know about neural nets. And mathematically, we can write them as this kind of system of equations, right? So at the first layer, right, which is xi of 0, right, that's my input image. Right, and then every time the time jumps, the time index is going to be discrete. Right, time corresponds to the layer. Right, so every time each layer computes a very simple light matrix multiplication followed by addition, computing the coordinate-wise nonlinearity and multiplying by another matrix multiplication. Right. So okay, so that's as much as we need to know, and there was a little bit change sometimes in 2015, right, where people moved from this model to this model, which is called residual network. So the only thing that was changed is that instead of setting xi t plus 1 to be the nonlinearity, they said, all right, let's just update the previous xit, right, the previous layer by some additive, right? So we keep the previous thing and we just add a little bit, right? So when I talk to my math friends, right, and physics friends, they usually immediately say, well, this is such an absolute change, right? Who cares about this? Well, I usually tell them there's 173,000 reasons, to think this is not such a trivial change, right? And actually, at MIT, we just hired the first author of this paper.
But is this something that is just the way we describe it, or there has been actually a change in the code that reflects this?
Yeah, of course, right? So they literally just changed, So the problem was that when let's say you start with random initialization for this kind of system, then when you backpropagate the gradient, it dies out quickly. And you have to do very careful tricks, right? But when you have something like this, right, you have the identity
following more inertia.
Yes. So there's So basically, this system they could train for like 10 layers, and if you're an artist, you do 20 layers. But this system can do 400 layers. and it just still trains. I'm not an expert in this. I'm just telling you what the original motivation was. But I think in the math community, the reason it was liked is because once we see incremental update, right, we can go from a discrete time, which is typically, again, you're a control people. I understand for you, both of them are simple, but for me, continuous time is a little bit easier to think about, right? So we can go from from the discrete time system to continuous time system, right? So basically now your so your neural networks, right? If you do this change, this is called neural ODs, right? They become parametric flow maps, right? And now you can think of this as a control problem, right? You have ability to steer in time, right? Again, time represents the layer here, right? And you can steer these representations, right, through the evolution. So that's a trick we're going to apply later as well. But in principle, again, this is not related to my talk. This is just a little bit of background. Okay, so now my talk is motivated by this, appearance. So as I said, this is some kind of major innovations in machine learning. So in the transformer architecture appeared in 2017, right, by a few people from Google, and they completely changed the world of machine learning. Today, all the modern things you see in the news, they're all based on the transformers. Including, now robotics is using transformers, generation of images and videos, all this is based on transformers. Okay, so what is new in transformers? So, as I tried to explain before, right, the neural networks, usually you just feed all the data as one stacked vector. Right? The change in transformer is that if you want to feed the sentence, for example, right, the idea was to convert the sentence into a sequence of words, right? They are called tokens, so sometimes they break the word into two subtokens, right? And then what you do is you have some kind of fixed map, right, which represents the word they by some kind of specific vector in d-dimensional space, right? And the beauty of transformer is that it views this sentence not as a one-stack vector, right? You could now have n times d-dimensional vector, right? If you just stack all these representations together. But what's important is the transformer really looks at this as a set, right? So it's a constellation of points, right? And it's a transformation map between constellation of points, right? It's not point clouds to point clouds, right? Yeah, so that's so from now on, whenever I talk about tokens or particles, what they really mean is they represent typically, the words in a sentence. And if you're more interested about images, then the image actually works similarly, except that you cut the image into little squares and you go whatever like this in this fashion.
And if I may, so one of the things that I just learned this week, which I didn't know before, that really the transformers don't remember any concepts in any full word, but only these segments of words, right?
In the sense,
yes, like brown, right? It's kind of broken up into tiny places. Yes. So when you talk, because you're talking about these tiny pieces of
yes,
it's even more remarkable. Right, they don't have actually single words as tokens.
But there are 30,000 of them, and in Google's modern model, it's 256,000 of them. So in some sense, they encode everything. Like, for example, my name is pretty atypical, right, for the English language. I mean, last name, Polyanskiy, actually the first name, Yury as well, right? So it would encode it as many tokens, right? But something like John would be definitely a token.
I see.
A dedicated special.
Yes, because my name was broken into 3 different tokens. I kind of check it because the ChatGPT gives you the tokenization. Right?
Yes, that's right.
And so I was very surprised. It doesn't know. It just knows 3 segments of my name.
Right. So one thing I should say is that, of course, the order of the words is important.
Yeah.
Right. So when you encode the word, you also say, by the way, it's not just the word there, but it also appears in position 1.
Yes.
Right? So these particles, they of course. Yeah. So in this sense, kind of the engine-defined transformer operates not on a sequence but on a set.
Yeah.
So that's the type I should have set, right? So the order does not matter, but you can encode the order if you want some applications at some point. Okay, so now how the transformers actually get trained? Okay, so there are played with different ideas, but in the end, transforms it into another point cloud, right? And after T iterations of these transformations, you get some other output point cloud, right? And they take typically only the last element, the one which corresponds to the trajectory of the n-1st particle, right? You take it and you try to predict the next one. And the system is constantly, given punishment or sugar, right? Depending on whether it predicts correctly or not, right? And after playing with this game 1 trillion times, you get ChatGPT, right? So roughly speaking, that's the idea, right?
And how long is that vector?
What is the
length of that vector that it's actively remembering for this prediction?
Excellent. So, okay, so again, it's a trade secret, nobody knows, but from the published data, it seems that OpenAI's the ChatGPT is about 100,000, and Google's new model is about 1 million.
I see. And I think the Google CEO just spoke about it, that they have a million model, but it doesn't give them much extra, right? It's very costly to run.
Okay, so you're asking about things which I'm not an expert. Like I know about this, but I know about this firsthand. So OpenAI has a smaller what's called context window, which is 100,000, but they have a lot of tricks how to use it. Because why do you need more context window? Typically, you want it, for example, to upload a book and ask questions about the book.
Yes.
Right. Yes. So what OpenAI does is they do a trick called wrap. I forgot what's that. But basically, what happens is they cut the document into many pieces, and there's a separate system which tries to, figure out which of these pieces the question corresponds to, and then it feeds only that piece. So I mean, tricks like this, they've been optimized for a long time. But Google somehow works with just a whole million. So, I mean, for example, it takes 1,000 tests where the answer to the question depends on like one part of the book connected to the middle, connected to the end, right? So people plan such questions, right, in the text, and then Google can do it and OpenAI can. Interesting, right? So in this kind of things, it's all this way. Anyways, it's completely unrelated to anything I will say, right? Because, okay, so I'm an information theorist by training, so I have to include Shannon in every talk. So let me just say that Shannon's very first paper, 1948, starts with the question: how do you model language? This was completely groundbreaking back then because thinking of language as a random process was out of this world, right? And in particular, Shannon specifically played this game where he tried to model the language as a predictive model, right, which generates the next word based on our previous words, right? Now, so this is kind of like a Markov model, but what I wanted to say is that this is a very special Markov model. Why? Because this function f is very sensitive, right? So when you generate the next word, right, this function f can have high sensitivity on one of the previous words, right? For example, early transformers were fooled by including the word not somewhere, right? You include some word not, right? The quick not brown fox jumps over from later on, right? And then it completely changes, right, the meaning because the fox no longer is brown, right? But it's just one word, so right. So anyway, and the question is always, for this continuous systems, right? It's a mystery. How can a continuous system, perform this large logic induction over many, many steps, which you see when you play with ChatGPT, right? So, and so this is a cartoon example, right? So let's consider the sentence: dog barking under the tree. So before transformers, typically what you do to analyze the sentence, right? In machine learning, you think about each word, as you embed it with, using the graph kind of co-occurrences, right? So, and if you consider the word bark, right, and you ask this kind of system, what does it correspond to? Right? It will say, well, okay, the word bark very often occurs with dogs, right? And it very often occurs with trees, right? Because it can relate to either, right? So kind of system, old school system, right? I mean, it can't want that, but the human, right? And you're not confused, right? You know bark and tree related, but in this sentence, immediately it's related to dogs, right? So somehow you have this hard kind of decision making, right? And this is our thesis, right? So we tried to, we started this project 2 years ago, right? By thinking, okay, how can these things reason? They must generate representations which, cluster the representation of these words together, right? And that's the hard cluster, right? It becomes 0-1 kind of inference. Again, it's not supposed to be a mathematical statement. This is more for like motivation how we get here. Okay, so now we're going to be mathematical. So let me now explain. So I purposely avoided explaining what transformer doing inside its guts. So now let's explain it. So it consists of 3 main components: layer norm, self-attention, and feed-forward. Okay, so how does it work? So if you have, right, so again, we're thinking of evolution of a collection of particles, right, in d-dimensional space. So what you do first, right? So you have current position of ith particle, right? So then you apply this strange operation, which is called self-attention. We'll talk about it. Then you normalize the output using something called layer norm, and then you update the position of the particle by this change, right? Okay, so after you do this, this is like half step, right, of the procedure, and then to make the full step, you also update your position by applying some non-linearity. This is called feed forward. Okay, so what is self-attention? So, you know, thousands of papers are claiming, and we are one of them, right, that the main part of the transformer is not a feed-forward part, it's a self-attention. So how does self-attention work? Okay, so self-attention evaluates the following tiny function. So it computes, so the ith coordinate of self-attention computes the following thing. So you convert xi token into qxi. This becomes a query vector, right? So this is fixed throughout the summation, right? And then you compute inner products with all transformed, right? So K is called key matrix, right? Key matrix acts on jth positional token, right? You get J, and then you compute this inner product. So some of them are going to be high, some of them are going to be low, right? So then you do softmax operation on them, right? Meaning just compute this partition function, right? To normalize it. So this becomes a probability vector, right? So from the point of view of I particle, the relevance of different particles is weighted by this probability vector. Then you average positions of those particles, right? So it's like voting system, right? When the particle decides where to move, it does weighted average of the positions of other particle, where weights depend on the positions themselves. Right? So that's the important picture. So.
Question.
Yes,
so
of course.
earlier you presented this image that the way the transformer works is that it always predicts the next one.
Yes.
Right? But here you have a vector and you're predicting on all the vectors. So did I miss something? Because not like you're predicting the next word, you're predicting the state of the vector, right? Or this is actually predicting the next word.
Yes, okay. So you should think about it this way. So you have a sphere, right? And you have positions of particles in the beginning.
Yes.
So then they evolve, right?
Yeah.
And n minus first particle, right, will travel somewhere, right? And it will end up somewhere.
Yeah.
Okay, so then you say, okay, where did you end up? Right. Let me try to interpret your position as a vote towards, you know, possibilities towards one of the 30,000 possible next tokens, right?
I see.
So that's the role of this decoder map, right? So that's another little neuron.
I see, but are we now trying to predict the next word?
Yes.
Or we're trying to predict, oh, so we are trying to predict
Yes,
the next one. I see.
And you're actually trying to predict the probability distribution.
Gotcha. Okay.
So for example, you say probability distribution of dog is, you know, 1%, and then the next token is dog, you're going to suffer a giant loss. As you said, it's very unlikely, but it did happen.
I see.
Right. So that's called the
I see. So the
percentage of the
xn is really the next word in the sequence.
Yes.
And this vector is always fixed.
Right. Oh, I'm sorry. Okay. I see. So the confusion is because I use n as a number. n minus 1.
So like the layers
Sorry.
versus the time, right?
Yes. Sorry, I should have used n here, and you're really predicting xn plus 1.
Okay.
Which is not part of our evolution of the, you know, of the particles. Yeah. Okay. So, right. Okay. So let me show you now. You know, I showed the thesis, right? So is there any way to hide this thing?
Yeah, there is. There was a height in there actually, on where you clicked earlier. It says height floating.
Oh,
There was there almost under.
height floating between controls, right?
Probably that's it.
Okay. Okay. Yes. Thanks. Okay. So now, how can we verify, existence of clustering? So what we did is we took this, pre-trained transformer. It's called Albert. So it's available for Hugging Face. We gave it an input, actually, Wikipedia article, right? I forgot, actually, I remember Magna Carta. It was a random sample. But, now what we are going to do, we will plot the histogram of the inner products, right? So these are, I forgot to say, layer norm actually places the particles on the surface of the sphere, right? So the inner products are going to
Just tokens.
Tokens, that's right.
Yes.
Yes. So representations evolve on the surface of the sphere.
Yeah.
So the inner products are between -1 and 1. So this, right? Okay, so at layer 0, so this is the initialized distribution, right? So you can see it kind of corresponds to some kind of random sampling, right? So it's a very nice shape, like kind of like Gaussian. It's not Gaussian because you sample, it's inner products, right? You sample that. And okay, so right. So this is the, there's nothing funny here. And let's see how it changes, right? So let's look how the evolution, how this Wikipedia article gets processed through the transformer. The embedding dimension here is, I think, 2048. So it's a giant dimensional space. Okay, so layer 5, we see this thing happening. So we see some number of orthogonal tokens here, right? So some tokens became orthogonal pairs, right? So probably 0. Okay, so and then as this thing evolves, right, at layer 10, you get this. You can see the probability distribution start to shift, right? So this means they're coming closer, typically, right? And so, but the most hilarious part is that at some point you can see some breakdown, right? So before it was kind of evolution of some smooth type, but now you can see that things start to break down, right? What you see is that this is emergence of clusters, right? The inner products start to have this shape, right? At layer 30, you have this, and you can already see a large spike. This means some particles have inner product exactly 1. This means they're already clamped together, right? And at layer 35, you have this, 40 this, 45 this, and 48 this, right? So this is, a proof, kind of empirical, right, that the real transformers do have several effects. First of all, the skyscrapers, they correspond to, once you have formation of several clusters, right, the inner product between them, right, you have 1,000 particles, right, if you split in 7 clusters, right, you will have 7 choose 2 different, right, so that's what this skyscrapers correspond to, right, it's a geometry between clusters, right, and this is the existence of the cluster, right, so this is completely empirical fact, right, so, and the whole topic of this project was to try to prove it rigorously, right, to try to understand how, how does it happen that transformers, this nice continuous system somehow want to marry particles together. They don't fly around like in Hamiltonian, right, conservative system. They would never hug each other, but something here makes them hug, right?
So can we go back to the interpretation? So you put one paradigm there.
Yes.
And then that's just the text, right? With a few thousand or a few hundred words. And then you are this cluster. So what's your mental image of what these clusters are?
Good. Again, it might have completely nothing resembling reality, but my opinion is that this is words which, for example, correspond to the same story of life, right? Or something like this. I mean, I would say probably some different order, like this is a giant vector. So probably some positions of this vector correspond to storyline. Some other positions correspond to, I don't know, who knows.
But you could look into the data and see what they are.
I could, yes.
Yes.
I didn't think of doing this. That's a good idea. Yeah. Right. This is more like semantic people, right? So there's a lot of work people try to do surgery on transformers. So I think that's actually, thank you for the suggestion that I can offer it to our
NLP
NLP guys.
speaks and then just highlighting the text of what they correspond
Yes,
to.
that's an excellent idea. Right. Cross my mind. Again, I view this more as like, funny empirical kind of test. Right. Okay. So, right. So this is the summary, right? So we saw at layer 0 some nice continuous distribution, and right, and then it becomes obviously exhibits some kind of. Okay. So now, how to make some mathematical sense? Okay. So this is my mental image, right, how practical transformer looks like. So there's a lot of special things and bells and whistles, right? So my goal here is to simplify it and make some abstract model, right? But of course, I don't want to simplify too much, right? I want to simplify so that we still retain cluster. So for the rest of the talk, I will try to show you some kind of the simplification steps, right? Which hopefully will motivate this kind of model. Okay, so let me show you the first attempt. So we're going to do 3 simplifications simultaneously. We're going to remove feed forward, remove layer norm, and we'll switch to continuous time. Just like I said for the neural OVs. So the people who did this, I mean, it doesn't matter, but we learned about this after, right? When we started doing these talks. So it was already known, right? This is called synchromer. It's a very nice paper by people who work on this, I think. So they did exactly this, right? So what I'm saying, right? So you rewrite this evolution equation in continuous time. So this is your self-attention matrix, and you grow feed forward. So this is what they got. They also got read of the layer 1. Okay, so they, I don't remember exactly what they proved for this system, but in that paper, but what's important for us is that we also analyzed it in our Yury paper 2023, this particular version. We started with this tool, and it turned out that this is too simple, right? So in this, for this system, you can kind of see that, it's kind of like x dot equals vx evolution, and, the system, tokens either fly to infinity or they go to zero exponentially fast. So, you have to play some special trick. So this is too much simplification. So let's undo one step, right? What we want to do is we want to retain the norm, right? So this means when our tokens, right? So remember, this is a summation, right? Which tells which token I want to, it's a force which drives me to some kind of weighted average of the positions of other particles, right? So if I don't want my particle, ith particle, to leave the sphere, right, I have to project this vector to the tangent space on the sphere, right? So then it will glide on the sphere, right? And this will retain normalization, right? So this is our change, right? So instead of considering, tokens which live in the d-dimensional Euclidean space, they now live with d-1 dimensional sphere, right? Okay, so now that's the first simplification. Okay, so now again, my math colleagues, right? I mean, they're very excited about the following. So they said, well, the first time we did it, they said, "Oh my God, this is amazing! This is a mean-field dynamics." Okay, so when they say this, what do they mean? They mean that for me, the mental image I have is that this is n particles, right, and they evolve somehow, right? But if you represent the particle system, right, by an empirical measure, right, then you can say that this is an operator, right, taking an empirical measure at time 0 and propagating it through space, right? Okay, so and this kind of dynamics, right, where you have the velocity of the particle, right, so you have a vector field which itself depends on the probability distribution of the particles, right? That's what you call mean field interactive particle system. So the beauty here is that you can write down some what is called continuity equation, right, for which basically extends this particle dynamics to measures. So the only reason I'm mentioning this is because some open problems are actually related to this. So we don't prove anything about this. So it's funny that you can do this. And if you're motivated by nonlinear PDEs, this is some of the stuff I'm talking about here. Give rise to some unstudied PDEs about which we have strict conjectures. So, but if you don't understand this, this is completely not important. Okay, so right, so we did simplification. So let's see if our model and still cluster, right? And let me just explain one more thing, right? So when I write this, because different layers of transformers apply different operations, right? Q, K, and P matrices can depend on time, right? So that's in real transformers they do depend on time. Right? It's kind of like time-dependent control.
So that's it. But in real transformers, we don't have 48 layers, right? So like, how did you create those Qs and Ks? Did you create? You do have 48.
Yeah, you do have sometimes hundreds of layers.
I see. Okay. Yes.
What we analyze is right? Yeah, because we have infinite discretization. But we think that for motivation, the discrete time jumps kind of similar to yes.
Conjecture for the PE you showed as well.
I'll show you the conjectures later. Yes. So okay. So right. So okay. So what I'm going to do now is I will simulate the system, right? Because on 3 dimensions, right? But I have to select some of these matrices K, Q, and V somehow, right? So let me choose them randomly. Right. So what I will do is this will be a piecewise random control, right? Sample from IET Gaussian matrices, right? Let's see how this thing behaves. Right. So this is the evolution. Right, so you can see that there's lots of strange movement for these particles, but you cannot deny that they kind of tend to come together. Right, some of them come together and they see that. So that's again, this is say from the beginning, right? You see, so the system is jittering left and right, right, but the particles do come together.
This is your random V.
This is random KQ. That's right. So okay, so now. The problem here is the following. We can't have, we don't have any theory to understand this. So we have to simplify a little bit more, right? So we know this is happening, but we have to simplify a little bit more, right? Let's keep doing this. So the next simplification is going to be to take PK and Q as controls to be constant, right? Fixed in time. Now, this is not unheard of. Again, this is not something that, is never done, because to store many of these matrices, right, we pay price of parameters, and actually exactly the one I'm using, it does use fixed KQ and V. And that's the reason we chose it. I did not actually try to plot the same histogram distributions. Not because it doesn't work. I know that you think that I maybe cherry-picked it. I just didn't try it because, when we started doing this, we could analyze this case. We started Googling, does anybody use this? And And so it turned out that, yeah, this is one of the models. So from that time, we always use algorithm. But that's another open question. Can you see clustering? Okay. So, right. So now let's think about right, KQV as fixed matrices, right? They don't depend on time. Okay, so we have this equation. So here's the first cool theorem. It turns out that under the assumption that you see, notice that everything in the system only depends on K transpose Q, right? So K transpose Q happens to be a symmetric matrix, right? This is the inner product, right? So, and it's equal to V or minus V. So that's a very special arrangement, right? So then it turns out something amazing happens. The vector of this, of this n particles is a gradient flow, either ascending or descending, for some energy functional, which is written like this, right? So this is telling us, right, that at least in this special case, our interacting particle system is attempting to, let's say, maximize this energy or minimize this energy, right, depending on the sign of B. So there's one very important trick here is that, which sort of we're very proud about, right, is that when you compute this gradient, right, so notice that this is an energy functional, right, which is defined on a product of n d-1 spheres, right? So it's a manifold. For example, when n is 2 and d is 2, this is a torus, right? So it's just a standard torus, right? So when you compute this gradient, you have to compute it with respect to crazy metric, right? It's not a standard metric on the sphere. We have to cook up some special metric, and then it turns out to be a gradient. Okay, so what good things does it give us? Okay, so let's see. So one good thing it gives us is that, yeah, so if you write down this equation in terms of measures, right? So then it turns out that this continuity equation, because we proved that the particle equation is a gradient flow, this means this PE is a Wasserstein gradient flow, right? For some energy, for some functional methods. Right? Again, we were super excited about this, and then when we proved this, I asked my math friends. I said, "Okay, now tell me all the great things that which follow from this." I hope they're not going to watch this recording, but they said they're not. It's amazing. It's very exciting. It's going to make us very very popular in the circles of analysts, but it absolutely doesn't imply anything. So anyway, so let's keep going, right?
Don't we love math?
Yes, right. But somehow so anyway, so like one of the famous things which were derived like this, if you replace this with entropy, right, then the Wasserstein gradient flow is a Fokker-Planck equation. Right, so this was a big field medal winning work, right, by Delaney. So it's kind of cool that we have some kind of gradient flow, but again, it doesn't tell us much. So let's keep simplifying. So what's the next thing? Okay, so the next thing is going to be completely crazy, right? We not only take V, K, and Q constant, we're going to take them identity, right? Okay, so that's right. So okay, so first of all, then the dynamics becomes very nice, right? So you see it's. So we have xi dot, which is again a tangent vector, right? Which is computed by simply the sum of inner products, right? Sum of weighted xj's, right? And the weights are now, there's no K and Q matrices anymore. So the equations are nice, right? But the main question is you should be asking, okay, do we still have any interesting dynamics for this, right? We throw, there's a Russian saying, right, that you can throw away the baby with the water. Right, so let's see if we threw away the baby with the water, right here. So right, so here I'm going to do simulation in actually in 2 dimensions, right? So this is I initialize n particles, 64 particles, right? I take beta to be 5. It's this special system, right? It's completely symmetric, and I'm going to start and make them run. And here I plot the histogram of pairwise distances. Unfortunately, this is not inner product, so this is distances. So it's like arc length, right? So 0 means cluster, right? Okay, so let's make it run, and we'll see some interesting effect here. Again, this is right. So we see that right, the system has some kind of interesting behavior, right? Even this very simple system already has clustering, and it's no trivial clustering. Okay. Any questions so far? Okay. Yes.
Maybe you'll get to this later, but is there something preventing clusters from overlapping in this case? Is it due to the initialization?
overlapping.
These three clusters just being the same, one big cluster.
So you're saying why they're not forming one cluster? Why are they splitting into three?
Yeah.
That's a great question. We absolutely don't know. Yes. You later, I will prove to you that actually, the funny thing is, if I let it run for the time which is comparable to the lifetime of the gas, they will all merge. These things don't merge completely. There's some infinitesimal precision, right? So that you can prove that the particles will never be in the same position ever, right? Right. So they keep. So they okay. Excellent. So let's look at this. This is the same thing, but for 3D, right? So right. So this was the example, right? So you see it's a little bit. It's going to loop. Right. So once again, see in this case, it's a large system. If you keep running this, all of them will work. But the reason for I put this slide here is I wanted to show so that not only we still keep having clusters, we also discover interesting phase transition, right? For betas, we have weak convergence to a single cluster, right? And for large betas, it seems that we have different many clusters. Okay, so let's keep this in mind. Right. Okay. So let's keep analyzing this what I call simple former. Right. So this is a transformer with this completely simplified dynamics. Right. So as I told you, it's a gradient flow, right, which is attempting to maximize this energy. Right. Sum of this summation over ij into the beta inner products. Right. Now because xi and xj are unit norm, right, you could equivalently say that my energy is given by this, right? It's a weighted negative exponent of negative distance within square distance, right? So it turns out that this energy function, right? So now think about this. This is a energy which score, right? Which tries to evaluate different point constellations on the sphere, right? So it turns out there's a very famous energy, and that's a very famous question. So extrema of this kind of energy were in particular studied by Henry Kohn in this paper 20 years ago. So what they've shown is that the extrema, so even though it looks simple, right, you could think, well, why don't I go home and try to prove what are the stationary points of this, right? If it's a gradient flow, we have to study stationary points, right? So it turns out that this function has crazy many extremas, and they're connected to something that I love and we used to work a lot on, to basically optimal error correcting poles. So every optimal symmetric error correcting pole will be an extrema for this energy function. Oh, okay. So, but you can also see one obvious thing, right? That there's a one global minimizer, right? You want to minimize, maximize, right? You want to maximize this guy, right? You want to put all these distances to 0, right? And that's very easy. You just take them all equal, right? And you cannot beat this, right? So this is a funny energy, right? So we see that there's a lot of saddle points, right? And local minimum and local maximum, but there's only one nice global maximizer, right, which corresponds to one cluster, right? Okay, so the next natural question is the following. You could say, well, here I have a dynamical system with interacting particles. We learn it's a gradient flow which is trying to maximize this energy. We learn the only global maximum is this one, right? Can't we conclude that all of these particles live in infinite time, right? Will converge to that? The answer is no. Of course, yeah, it's obvious for some, maybe less obvious to others, right? That because objective is not convex, right? You don't know anything about this, right? Gradient flow can actually cycle, right? Can have some asymptotic attractors. It may get stuck in some spurious maxima. It can get converged to saddle points and so on, right? So, okay, so what can we do? Are there any questions so far? Okay, so
just a quick question.
Yes.
So when you do the flow maximizing the energy, do you impose it on the sphere, or you just...
yeah, of course, yes. So everything is defined only for configurations on the sphere, right? Yes. Okay. Right. So okay. So let me show you one result, which actually doesn't require me to take K and Q to be identity, but only V should be identity. Okay. The result is the following. It says that when you have number of dimensions bigger than the number of particles, and for every beta, and for IID uniform initialization of tokens, you will converge to the same. So all the tokens will converge to one point, right? So here's the illustration of this effect, right? So okay, so how are we going to prove this? Okay, so first of all, so suppose my initial tokens are all in one hemisphere. So let's look at the dynamics again on the previous slide, right? So if the ith point, right, is the direction in which it wants to move, right, is a complex combination of positions of others. If they're all in one hemisphere, right, then the cone that we call it the cone collapse lemma, right? To draw a cone, right, for the configurations of all particles, right? Each particle wants to move inside the cone, so the cone should collapse, right? So it's a natural thing. Okay, so then why is d bigger than n? Well, we can easily check, right? That if you have more dimensions than particles, then you can always include them in some hyperplane, right? And this hyperplane will miss the center, right, of the sphere. So it means they have to be in some hemisphere, right? Okay, so that's a nice, this is our first rigorous result, right? So we see that if dimensions are large, then you definitely converge to single.
And the beta larger than zero is a statistical mechanics interpretation. That's kind of the low noise level, right?
Yes.
I see.
Wait, so beta bigger than zero means in all noises, right?
In all noise. This is for beta, so it's not a critical grade beta.
Yes, there's no criticality. That's right.
It's all base.
It's all beta. Okay. All right. Yeah, so it's completely right. Thank you. Okay, so right. Okay. So how we go? Let's go back now. So what we need to show, right, for the evolution of the system in general, right, is we want to show that, because remember, we also cluster in dimension equals 2, right, and 64 particles. So that's not captured by the previous theorem, right? Okay, so then what we need to do, right, is we already see cone collapse, right? Happens once we can prove that these tokens are all in the same hemisphere. So that's the only thing we need, right? In the two-dimensional case, we just want to prove that eventually they get inside one half circle. Okay, so now here's where I need to quote some standard results in gradient flows, again, which I didn't know before the beginning of this program. Gradient flows can cycle. There's a famous example called Mexican hat. Again, so experts here would know this, right? Where gradient flow actually keeps cycling and never converges, right? But Vlahosevich proved that if your energy function is real analytic and you're on a real analytic manifold, which we are on, then gradient flow must converge to a stationary point, always. Okay, so this is good. Now we need to just classify what kind of stationary points we can converge to. Again, there's a general theorem which says that, right? So imagine you have some kind of saddle point, right? So you have a point such that you're trying to maximize, and then there are escape directions which would maximize you, right? And then some directions which are in which you are right, in which you are local maximum, right, along this. So it's a saddle point like this, right? So right, so stable manifold theorem says that the set of points for which you can converge to this point, right, to a saddle point, right, has codimension 1, right, or more, right, which means generically you can never hit it, right? So the only thing we are left to prove is that every stationary point, of which there are crazy many, right? Remember, there are super crazy stationary points for this energy functional, right, which are all this group theory kind of based constructions. But we need to prove that for every stationary point there exist escape directions, right? Except the one global maximizer, which is everyone is synchronized. Okay, so how did we do this? Before I tell you this, let me show you some of the coolest moments in this project when we realized that actually we are studying a generalization of something that got lots of recent attention, right? So let's again look at this model and let's take beta equals 0. This is a high temperature G, right, where tokens don't interact much, right? If you take beta to be 0, then all these weights are 1. You normalize by n, right? And so you see that actually this vector which drives evolution of the system is the same for all particles. Basically, what the system does is it computes the mean, right? So you have n particles in the sphere, right? You compute the average direction of them, right? And then you drive every particle towards there, right? But of course, after projection, right? So each particle goes towards its mean, right? It's a very, very simple model, right? It has a name, it's called Kuramoto oscillator model, right? For dimension 2, for dimension bigger than 2, I think it's called Loki oscillator. Some people still call it Kuramoto model. Okay, so for such a simple system, you would think it's super easy to prove, right? If all particles constantly go to their common mean, it's very easy, right? But the system was introduced in somewhere in the 70s, and the rigorous proof of synchronization was only obtained in 2012, right? And for Loki oscillators, if I'm not mistaken, I think it was altered for our work. Okay, so how are we going to prove this? Right, and again, I don't know if anybody did anybody hear about Kuramoto model? Am I reaching those? So
in our community, that's a very
okay. So yes. So I should say then you probably know that there is extra oscillator, right? So that you also can oscillate, right? So you also can oscillate, right? So each oscillator has its own natural frequency.
But in this case, you have identical systems, right?
Right. So this is called homogeneous Kuramoto.
Yeah. So actually, there have been many results in synchronization. I don't know about Taylor, but there have been many results in simulation for identical systems.
Right. Okay. So again, I mean, to the best of my knowledge, I tried to trace this theorem. I think this is the first guy who proved that. Okay. So let's.
The point of the Kuramoto, there's a phase transition there, right? From
yes,
synchronized to
right,
non-synchronized,
yes.
Given the different frequencies. But
right.
you have the same frequency there.
So they are always synchronized.
They're also that, but aren't they synchronized by default? Then in that case, if they have the same, oh no, you still need to do interaction between them to do that.
That's right. Like that's what I said, right? So there were partial proofs before this guy. There were lots of partial proofs which would prove that it converges to the one of two configurations. It's like everybody here, and maybe some people go to the antipodal point. So our contribution of this guy
because it's on the sphere.
Yes.
Okay.
Right. So that maybe that's the
It's on the
part.
sphere.
Yes.
Sphere maybe mistake.
So right, what this guy did is no, but it's also in a circle, right? So you could prove that, So what they could prove is that the system should converge to, all the particles are an antipodal configuration, right? But what you really want to converge it is that they all converge to single touch. So I think that there was this and for the sphere as well, for proofs which prove, but not in complete generality. So okay, so let's talk about 2D case. Sorry, I think I'm a bit okay. Right. So we'll do parameterization in terms of thetas, and so then you get this equation, right? So SA stands for self-attention dynamics, right? And as we said, this is gradient flow for this energy functional, right? It's just now expressed in terms of thetas. I think it's it's more natural. I love this kind of system. It's very simple. Okay, and if you take beta to 0, then this becomes a Kuramoto potential, right? So the Kuramoto models, the particles, right, sitting on the sphere, on the circle, right, they're trying to minimize the sum of cosine differences, sum of cosines of differences. Right, okay, so what we proved, right, is that for all dimensions, and for beta less than c over n, or beta bigger than c times n squared, any stationary point of the energy is strict sum. So there exists an escape direction, right, except for global maximum. And as I said, by general properties, right, this implies that because we have a gradient flow with a simple former, we have convergence to a common single cluster. Right. Okay. So I have some proof sketch. Let me skip it for now. Maybe if there's interest, I'm happy to stay here. No, it's a fun proof. I'm really happy to show it, but let me just skip it, and instead let me tell you what's missing, right? Okay, so so far what we achieved is we proved, because I also I promised to show some open proof. Okay, so why is this a cool result? First of all, you see it shows for both low and high temperatures, right? We have synchronization. We have a cluster, right? So we rigorously prove. Okay. We were very happy about this because kind of, I mean, we all believe that it happens for all data, right? But now we already put here, we put here, right? So there's no reason, there's a lot less reason to believe it's not going to be. So we're kind of waiting for someone to fix it, right? Or maybe us to fix it, right? Powerful technique. But then we realized one problem, right? That if we want to extend this to a statement about evolution of the measure from the PD, right? The nonlinear PD that I was showing in the continuity equation. And one strategy would be to discretize the measure and go to particle evolution. But you see, then N will be giant, right? And eventually we will leave out all betas. So in terms of measures, we don't know if it's true, right? We don't know if that PD, so our conjecture is that that explicit PD, right? Always, which is a Wasserstein gradient flow, right? Initialized from any distribution, right? On the circle, any smooth density, right? Will eventually converge to the delta function somewhere, right? So we don't know how to prove this. Okay. Sorry, I should say not every sufficiently asymmetric, right? Because if you start with a constant density, it will stay constant. If you start with a density which is, symmetric with, let's say, rotation symmetry, the rotation symmetry will be retained, right? So meaning some density which doesn't have, let's say, obvious symmetries in it. From a general, sort of like we do for general initialization, right? Okay, so this is one problem. Now, what is another problem with this? We were very happy that we were able to prove this. As I said, as a special case, it also proves something new even for Kuramoto model. Okay, so now we know that long-term we converge to one cluster, right? But not just here, I'm showing you, right? Not cherry pick, just two, first simulations for beta equals 1 and for beta equals 9, right? Our theorem predicts this two numbers, right? 1 and 9, which it does, right? And predicts that in long term, we will converge to one cluster. And this is what we see here very clearly by time 15. But here we don't see it, right? By the same time, whatever, 15, right? We have 3 clusters and they don't seem to be moving. So this is what we call metastable states, right? So they seem to be metastable states. So one way to, so how would we attack this? We have two ideas, completely don't know how to proceed at this point. So one idea is to try to right? So what happens? Your node has escape direction. It will go further higher up, right? By merging these guys. But that escape direction is very, very low, kind of velocity to it, right? So now we need to somehow have a tool, right? We need to upgrade our proof and show that somehow count, and show that as beta changes, right? The number, the density, or like the collection of subtle points, right? With very low escape directions, right? Starts to increase. So that's an interesting question, right? So if you know Katz-Rice formulas, maybe this is useful here, right? To count critical points, but we don't know how to apply this yet. So what I had a physics background, right? So I was trained in this physics. So one thing that came to my mind, well, this is an old school problem, right? But N particles, they all interact with each other, just like gas. Molecules in this form, right? But we are able to say cool things about them, right? Even non-stationary dynamics, right? Low equilibrium dynamics. How do we do this? Well, we need to consider law of some number of particles, right? The joint law, rho of R. And in particular for clustering, the only thing we really need is we need to understand the distribution of two randomly chosen particles, right? Okay, so we because the system is symmetric, right? We can as well describe that's right. Okay, so let me show you something that we call phase diagram, right? We don't have any. If you know something called Bogoliubov hierarchy, BBGKY, right? There is a method to analyze these kind of things. We're pursuing it, but so far we don't have rigorous results. So, but let me show you something that we've seen. So we started looking at this phase diagrams. So let's plot, right? This is a 2-point correlation function, right? Let's plot as a function of time probability that two random particles are, very close, epsilon close to each other. Right? This means their inner product is almost 1, right? So this function will depend on two things. It depends on time and it depends on beta, right? So okay, in dimension 2, you get this plot. So let's analyze this first, right? So what do you see here? So if you start with some beta 1, right? Then up until time about 6, right? You have blue. So this means probability of two particles being in, next to each other are it's very low, right? So it's very low, very low, very low. Then suddenly, there's this strange regime where it's constant time, right? So it's some kind of constant between 0 and 1, and then it becomes 1, right? So this means by the time 15 or so, right, the probability of of two particles to be in the same is 1, right? And remember, we're choosing random particles. This means all of them are there. So when this number is between 0 and 1, this means you have a few clusters, right? When it's 0, this means no clusters, right? So you can see that this gray zone, right, is the metastable states, right? Okay, so here's the next excitement about ours. So when we obtain this phase diagram, right, we could go in many directions. Fortunately for us, we went into the direction of high dimensions. So we started plotting these diagrams as t-scales, right? So we plotted for dimension 2, 32, 128, and we saw, this beautiful pattern. The phase diagram becomes 0, right? Okay, so we start. So can we prove this? We have completely a formula.
So does the 0 1 mean that there is a phase transition in beta then?
Yes, because you see, so
yes.
right. So for every fixed beta, there is a critical time, right? After which after all, right? So in high dimension,
the phase transition from everybody coming to one point versus having multiple.
No. Sorry, it's different. Yeah, so it means before this time, they're still not lumped together, and after this time, they're all in one cluster.
I see. Okay.
So in high dimensions, at least for this setting, right? So what this means is that there's no metastability, right? In very high, they go around and then they boom, collapse all together.
Go vertical.
Right.
In the beta space, then is there a phase transition?
Right. So this is what you're asking, right? So it's interesting that you see. Okay, so what you're saying is that the interesting stuff happens here.
Yeah.
And this little zone, so it's in the critical strip.
Yeah.
So
because it looks like even if you go to time infinity, it saturates, so there will be a phase transition in beta, right?
Yeah, we started this again. Our proofs show no.
No, I see.
Because our proof
goes to
applies, right? For every fixed beta, right? Eventually in time, we will have one cluster.
Gotcha.
I mean, okay, technically we only proved it for small beta and large beta, so it could be that the phase diagram is like this. But so so that's an all great question, right? But let me say one thing from the practical point of view. You see, so you probably don't want your transformers to work here, right? Because this means if you pass any input data, it always clusters into one point. So this is a bad regime. This is also a bad regime because it means your thing doesn't learn anything, right? This learns no associations. So this curve is very important because it explains that beta corresponds to something that is known as strength of initialization in transformers. And that is a very carefully chosen parameter. That's one of the secret sauce for people who train it. This is some number, and what this tells us that the more layers you have, the bigger this KQV matrices should be in the beginning. That's the funny kind of practical recipe, because you want your transformers to live in this regime, right? Because you want to steer this metastable states to where they want them to be, right? So that's like one of the things which kind of imply some stuff for the ChatGPT, so to speak. But okay, I guess I'm out of time. I just wanted to show that we have a theoretical prediction for this phase transition boundary, and it matches, and it eventually goes to here. Okay. Yeah, thanks. I guess. Right, so I'm out of time, guys. So thank you so much. Okay. The proof is actually not very hard. So, okay. So the idea is, we want to prove something about Hessian, right? So we write down Hessian, right? So it's some kind of, some kind of expression. So it turns out that you can prove the following thing. So G is some special function, cosine. I will show it in the next slide, right? So the positive semi-definiteness of the Hessian means that for every subset of particles, the following sum should be above negative. This is just applying Hessian to the indicator of S, right? So I'm only using 0, 1 test vectors, right, to check PSD-ness, right? Okay, so once you have this, right? So now we want to show that this condition is true, right? Okay, so then this function G, right? I mean, it looks like this, right? Okay, so what you see here is that it's only positive in the small strip, right? Okay, so right? So this function is positive, right? And you're taking the differences, right? Okay. And you know that this should be true for every subset, right? If the matrix is positive semi-definite, right? Okay. So then here's what we do, right? We say, okay, start with first a set which consists of one particle, right? Because right, and take S to be one, and this is all the other guys, right? If all the other guys were too far, you would only sum negative numbers. So this means at least one guy should be close to you, right? Okay, so now we have two particles, right, which are closer than tau, right? Tau is 1 over square root, right? Okay, so then we added this particle to our set. Now we apply it to the set 1, right? Again, we're summing something, right? This is summation over I belonging to S, right? It's one of these two guys, right? And then this J is over all others, right? If all other guys were farther than tau, right? Like this, you would again be summing negative numbers. So that must be that one of them is again closer than tau to one of these two, right? And so you're doing it like this, right? And then the total sum of if this is smaller than pi, this means right all your for every positive semi-definite stationary point, right, which is a local maxima, right? For every local maxima, all the points should be in one hemisphere. If this is true, this is the low temperature condition, right? Sorry, this is low temperature condition, right? That's the hard thing, right? And so and we already proved that there cannot be stationary points with all points in one hemisphere. So it's very simple. So for d dimensions, you need a super cool trick, which I didn't describe in the slides. It's in the paper. It's hard to explain. It's averaging over some skew symmetric Gaussians and the group, on the Lie algebra. So it's it's a really cool idea, which I'm very happy about.
Any other questions from the audience? I have a bunch of questions, but I'll keep it for the discussion afterwards. So if no more questions, then let's thank again the speaker. You didn't tell us about the Witcher model, or it's just a version of Kuramoto model. Don't worry, we can discuss it.
Yes,
let's give a chance to the audience to move on. But
I think one thing maybe I wanted to mention in the partnership. So those are phase diagrams for the simple form.
Yeah,
right.
Yes.
So I mean, of course, right? We also play in the following way, right? Suppose you take this is the most fun one, right? You take all of them are random.
Yeah.
And you see the phase diagram. It's totally different. We cannot explain it. What's more fun is that if you want to take one of these, okay, then phase diagram resemble our simple form. If all of them are random, then